Hello, everyone. Fine. Today we are going to discuss scattering theory, a wave mechanical approach. Wave mechanical approach is very important in quantum mechanics. Scattering theory is, in fact, very important theory in classical mechanics as well as in quantum mechanics. Many phenomena we observe surrounding us are based on scattering. Now, scattering phenomenon is observed in games also. The first picture shows the scattering taking place in billiard game. And whenever a one ball strikes, and it scatters the other balls. And that is shown in the next picture, that how the scattering phenomenon is observed. The second one is a scattering of light in atmosphere. We see beautiful colors of sky during sunset and sunrise, and that is due to scattering. And the second picture shows the scattering phenomenon taking place in atmosphere. The third picture shows the alpha particle scattering by gold foil. And that is a very famous experiment. And in that one, the alpha particles are bombarded on gold foil, and those are scattered in different directions and detected. And that is the tool to see inside the atom. And first, the nucleus was detected by this particular experiment. The second experiment is in that direction is the X-ray scattering. The X-ray scattering is shown over here. There, the small angle X-ray scattering, the X-ray is incident and scattered and recorded on the photographic plate. And the photographic plate is having a ring type of structure, and that gives a characteristic of a particular sample. Another is a high energy scattering phenomenon. There, electron and quark scattering is taking place, and this shows the picture of electron and quark scattering particular figure. And one more is again the high energy scattering phenomenon, where deep inelastic scattering at high energy is shown, and that is shown in a very popular experiment and a very prestigious experiment, that Large Hadron Electron Collider. So that is a huge setup, and that setup is shown in this particular picture. So it is a very high energy experiment. Scattering opens the window to look inside the atom or nucleus, depending upon the energy we have used. Now we come to the kinematics of the scattering process. A parallel beam of particles of a given momentum is incident on a target, which deflects or scatter the particles in various directions. The scattered particles diverge in different directions at large distances from the target. Their motion is considered radially outward and detected by a suitable detector. So in a block diagram, it is very simply explained over here. Incident beam, the target, it is hitting the target and getting deflected. So the process is shown with the three blocks, and that is simply explained a scattering process. Now, a coordinate system with origin at the position of the target or a scattering center is selected. So we select a coordinate system which is having origin at a target or scattering center. And usually the z-axis is taken as the direction of the incident beam. So we are taking a z direction as an incident direction. Origin of the uh, system or a coordinate system is taken at the scattering center or target. The directions of the scattered particles is indicated by polar angles theta and phi, and z axis is the polar axis. So that indicates that we are using spherical polar coordinate system to describe the scattering phenomenon. Now, this shows the diagram depicting the scattering phenomenon. This diagram is very important diagram where the incident beam is hitting the target and it is deflected in different directions. So different directions are shown by angle theta, and different particles are scattered in different directions. So ultimately it is making a cone. So particles are deflected in different directions. So suppose we think that the particle is deflected in this particular direction. So in this direction, particle is deflected. And we form a parallelogram, and that is showing a scattering plane. Now, there is another plane which is known as a reference plane. So reference plane is arbitrarily taken as a fixed plane, and that shows a particular direction of a arbitrary plane, and that is shown by a thick line, and that is again a parallelogram. So this by these two planes, they are forming an angle phi. So this angle phi is between the two planes. One is a scattering plane, another is a reference plane. Reference plane is fixed, but scattering plane changes with the direction of the scattering of a particle. Then the target is shown over here, and the incident beam is shown by this. Now, the scattering plane and reference plane, they are forming something like a shape of a half-open book or a notebook. So that is again shown in the left-hand side diagram in a 3 dimension. So 3 dimension left-hand side diagram is shown. That makes it more clear rather than the 2 dimensional diagram. Now, the angle theta is the angle between the scattered and incident direction, and it is called the angle of scattering. That is shown by angle theta in the diagram. These two directions define the plane of scattering. So the plane of scattering is shown by a parallelogram, and that is shown by a light line parallelogram, and heavy line parallelogram is showing the scattering reference plane. Now, the azimuthal angle phi specifies the orientation of this plane with respect to some reference plane having z-axis. So this is the azimuthal angle phi. Now, we come to another important part that is known as the flux. Flux is the number of particles crossing unit area taken normal to the beam direction per unit time. So this is the unit area, number of particles crossing that define unit surface area in unit time. That is shown by a parallel line. These are the number of particles crossing the unit surface area. If flux is independent of time, then it is a steady incident beam, and that steady incident beam is maintained for an indefinitely long time. There will be a steady stream of scattered particles. So here, if we consider flux is independent of time, then steady beam of particles, of incident particles is maintained. And there will be a steady beam of scattered particles. Now, in that case, let us consider, let delta n be the number of scattered particles in a small solid angle delta omega about the direction theta and phi, and that is taking place in time delta t, or a small time interval delta t. So this is the solid angle. Solid angle is defined by delta omega, and this is the surface area. This is the surface area shown, and the number of particles crossing the surface area, that is delta n, and that particular surface area is in the direction of theta and phi. And this is particularly shown in this particular picture. Now, if it is assumed that the flux is low enough to avoid interaction between the incident particles with one another, if we consider that flux is low enough so that there is no congestion of the particles, there is no bumper to bumper traffic like we observe in our major cities, but the particles are coming at a certain distance so that there is no interaction between the two particles. So flux is low enough. Then the number of particles delta n will be proportional to the solid angle delta omega, delta t and f. So number will be high if solid angle is large. Number will be high if you are taking delta t, time interval large. Number will be high if the input flux is high. So delta n, number of particles deflected in direction theta and phi, will depend upon these quantities. One is the solid angle. If solid angle is large, obviously the number of particles observed is large. If you are taking time interval large, then obviously the number of particles detected will be large. If you are detecting in 1 second and if you are detecting in 10 seconds, the number of particles will be large. And if the flux is large, then the number of particles deflected will be large. So that is shown by this proportionality relation. Delta N is proportional to delta omega, delta T, and F. Now, if we remove the proportionality sign, then it will be delta N equal to d sigma theta phi by d omega, delta T, delta omega, and delta F. So this is the proportionality factor because we have removed the proportionality sign. So we have to introduce a proportionality factor. The proportionality factor d sigma by d omega depends on theta and phi. You have already mentioned that d sigma and d omega depends on theta and phi. And it is called the differential scattering cross section. This has the dimension of an area and it depends upon the parameters of the incident particle and nature of the target. So differential scattering cross section is defined by d sigma by d omega. Now we come to the total scattering cross section. Now total scattering cross section sigma may be obtained by integrating over all directions. So sigma is equal to integration d sigma by d omega, we are taking all the directions. Now we use that 0 to 2 pi, that is for d phi, and 0 to pi d sigma by d omega sine theta d theta. Now in most of the cases, d sigma by d omega is independent of phi. And just we put the total limit 0 to 2 pi, full limit in this particular integral, then we can write sigma is equal to integral d sigma by d omega 2 pi sine theta d theta, and we name it as equation number 3. So we call it as equation number 3. Now we come to wave mechanical approach. Now we come to very important part of wave mechanical approach. Till now, we have used the particle approach. We consider the number of particles incident, number of particles scattered, and we detected the number of particles scattered in a solid angle d omega. Now they are using a wave mechanical approach. In this wave mechanical approach, we are considering that the number of particles, instead of number of particles, we are considering the wave. Then the particles involved in the scattering process are quantum mechanical objects. Then they are described by a wave function. So any particle can be described by a wave function in a wave mechanical approach. The wave function will be stationary if it is assumed a steady incident beam is maintained for all time. So we consider a stationary wave function when the steady beam of particle is maintained all time, or the flux is a steady flux. The phenomenon of scattering is considered as a distortion in the stationary wave pattern caused by scattering center or a target. So here we have depicted a diagram where the red is the target and incoming beam or incident beam of particle is considered as a plane wave. So plane wave is shown. Plane wave depicts the incoming wave or incident particles. And naturally, whenever the plane wave is hitting the target, it is converted into a spherical wave and it is propagating on the right-hand direction. So incoming plane wave is converted to spherical wave by a target. So first diagram shows the plane wave is converted into a spherical wave. Second is the second figure is the experiment one can do at our home also. If we take a shallow tray and take a very simple scale and we just vibrate a scale in a water filled in a tray. So first we have to take a shallow tray filled with a water and take a scale and vibrate the scale. So plane waves are produced. And in a tray, in a middle of a tray, put some object, any type of object, and try to observe that the plane waves are converted into spherical waves. So that is known as a ripple tank experiment. That experiment one can do in our home by taking a very shallow tray filled with water, and scale is vibrating periodically so that the plane waves are produced. So right hand side diagram shows the ripple tank experiment result. We can verify the nature of waves produced by that. Now at larger distances from the scattering center, at r tending to infinity, the form of a wave function ux contains the two parts. One is u incident and another is u scatter. Now, the function u incident corresponding to parallel beam incident particles, and another is u scattered, the corresponding to the scattered particles moving radially outward from the center. So, at a very large distance from the scattering target on the right hand side, if we see that ux is having two components as shown in equation 4, that one is u incident, that is a plane wave, and second is u scattered, that is the spherical wave at very large distance. That is shown by equation 4. So equation 4 shows this particular phenomenon. Now, beam of incident particles with momentum p h cut k along the z-axis can be described by a plane wave momentum eigenfunction. So incident particles having momentum p, which can be represented by h cut k, and those are moving on the z direction. So plane wave momentum eigenfunction can be represented as u incident e to the power I k z. Now this wave function is not a normalizable wave function. So first we have to make it a normalizable eigenfunction. So the incident flux is obtained by multiplying the quantity by particle velocity. So if we take a flux F, it is the modulus U incident square and multiplied by V, that is the particle velocity. So that becomes a normalizable function. And V can be represented as P divided by M. And P is represented by H cut K by M. So that is named as equation number 5. So equation number 5 represents the phenomenon taking place in the scattering. Now we come to the further derivation, considering that the scattering is elastic type, which means that the particles have same momentum after scattering and before the scattering. So the same momentum is there. It is known as a elastic scattering. Same momentum before scattering and after scattering. And the wave U scatter represents the scatter particles having the same propagation constant k, but have spherical wave because of these particles move radially outwards. So we consider that it is elastic type scattering. So the propagation vector k is the same, but only thing is that the after scattering, the waves become spherical one. Before scattering, the waves are plane waves. Now the types of waves are e to the power ikr and e to the power minus ikr, where the e to the power minus ikr is incoming wave and e to the power ikr is outgoing wave. So we have a two different type of waves. One is e to the power ikr, another is e to the power minus ikr. E to the power minus ikr is incoming wave and e to the power plus ikr is outgoing wave after scattering. Now if omega is equal to capital E divided by h cut, now we can establish this relation very easily, that E is equal to h cut omega and e to the power minus I omega t. Then the expression e to the power ikr minus I omega t shows the surfaces of constant phase. And this is the phase factor that shows the surfaces of constant phase. And that can be represented as Kr minus omega t. And it is equal to constant. And when move outward from the origin, and R is equal to constant plus omega t divided by k, increases with time. And that is why that is the incoming wave, another is outgoing wave. So that can show that how incoming wave and outgoing waves are defined. The scattered wave, U scattered, is moving outward and it is proportional to e to the power ikr. Also, the flux of the scattered particles decreases as 1 upon r square as distance r increases. So as distance r increases, the flux decreases by 1 upon r square order. Now, therefore, we can write U scatter is proportional to 1 upon r. So if we make it U scatter modulus square, then it is proportional to 1 upon r square. So this is a scattered wave function or scattered wave proportional to 1 upon r. This is the flux. So flux is modulus U scatter square, and it is a normalizable. So we have multiplied by V, and in other words, we have multiplied by H cut K divided by M, and that is the flux of the scattered wave. And now we have to put the value of U scattered. So we have put the value U scattered is F theta phi e to the power I k r divided by r, because here we have removed the proportionality sign. By removing proportionality sign, we have to add proportionality factor. So scattered waves or outgoing waves after removing the proportionality sign is shown in last equation of equation 6. Now, at large distances from the scattering center, as r tends to infinity, the form of a wave function ux must contain the two parts. One is the incident beam function that is represented by u incident corresponding to the parallel beam of incident particles, and another is u scatter corresponding to the scattered particles moving outwards from the center. Again, we come to that our particular equation, and that equation shows that two beams are shown by this particular phenomenon. Now, this can be represented by, let me come to the next slide. Yes, the dependence of the proportionality factor f theta phi on theta and phi indicates that the scatter flux is direction dependent. So we have defined in our earlier equation the proportionality factor f theta phi that depends on theta and phi or direction. The delta n in equation number 1 is nothing but the radial flux multiplied by delta s delta t, and it is represented as delta s equal to r square d or delta omega. That is the element of the solid angle normal to the area. Now, this solid angle is shown over here. This is S is represented as delta S, and this is the solid angle, and it is represented as delta S by R square. So this is shown by this particular figure. Now, we consider that area delta S is the area normal to the radial direction covered by solid angle delta omega. So delta S, here it is represented as S, but if you consider it as an element of surface area, then delta S, and this is the solid angle delta omega. and that is the surface perpendicular surface to the radial direction, which is covered by solid angle delta omega. Now, number of particles delta n, U scattered modulus square h cut k by m, r square delta omega delta t. Now, using this particular geometry. Now, delta n is equal to, now we are putting the value of U scatter. So, f theta phi divided by r square modulus square. H cut k divided by m r square delta omega delta t. And this r square will cancel out. So it will be delta n equal to f theta phi modulus square h cut k divided by m delta omega delta t. Now this is equation number 7. And we have already derived similar type of equation, that is equation number 1. And that is the number of particles delta n, and it is a proportionality factor, that is the differential scattering cross section d sigma theta phi by d omega delta t delta omega f. Now both of this should be equal to each other. So now comparing equation 1 with equation 7. So modulus f theta phi square h cut k divided by m delta omega delta t, that is equation 7, compared to equation number 1, d sigma theta phi by d omega delta t delta omega f. Now we know that delta omega delta t are there on the both sides, so cancels out. So it is ultimately f theta phi modulus square h cut k by m d sigma theta phi by d omega equal to f. Now we also know from equation number 5 that flux is equal to h cut k by m, that is equal to v. So it is this h cut k by m equal to f. So this is cancels out. So ultimately the remaining thing is f theta phi modulus square is equal to d sigma theta phi by d omega. And f theta phi modulus square is known as a scattering amplitude. And the right hand side d sigma theta phi by d omega is known as a differential scattering cross section. And this is named as equation number 9. This is named as equation number 9. Now let me come to next slide. Now this is a very important equation. Now we come to yes. In order to calculate the scattering cross section, one needs to determine the particular stationary wave function, which has the following asymptotic form that is required by equation 4 and equation 6. Now, equation 4 and equation 6 we have already discussed. Now, asymptotic condition we have to obtain, and that asymptotic condition is very logical and very important. Now, what we are going to state in this asymptotic condition, ux tending to e to the power ikz f theta phi e to the power ikr divided by r at as r tends to infinity. That is equation number 9. That is very important condition, and that is the condition to be fulfilled in most of the wave mechanical picture of scattering theory. Now, how that is depicted, that incident waves are a plane wave, and that is hitting the target converted into spherical wave. Now, if somebody is standing here at an infinitely large distance, I'm showing with an arrow, at infinitely large distance, if somebody is standing, that person, observer, will see two things. One, the incoming plane wave. Another, the spherical wave scatter. Now, at large distance from the scattering center, if one observes that two things will be observed, incident plane wave, another is a spherical scatter wave. And that is the thing we are normally observing in our day-to-day life. Suppose a light is coming from a far away place outside, and we are standing somewhere, then some object is scattering light, then we'll see the two things. One, light coming from a far away place. Another thing, the scattered light from an object. And we see each other through this phenomenon only. Because whenever light is falling on the human face, it scatters. And that light we are observing. Another thing is that we are observing the direct light coming from the source. So this is the natural phenomenon, but it is depicted quantum mechanically in this particular formulation. So if somebody is standing at a far away place, one can observe two things together. One is direct incident beam, that is the plane wave. Second one is the spherical wave, and that is scattered or that is produced by scattering target. So two waves are observed at a far away place. At infinitely large distance, one detects the incoming unscattered plane wave and spherical scattered waves. Both are detected as shown in equation number 9. So that is shown in a particularly blue box. The stationary wave function must satisfy the time-independent Schrodinger equation. So stationary wave function depicted by ux must satisfy the time-independent Schrodinger equation. So time-independent Schrodinger equation is given over here. It is named as equation number 10. And here E is equal to h cut square k square divided by 2m. Now I am coming to the slide which is depicting the early contributor. This is the photograph of Ernst Rutherford, born in 1871, died in 1937. He was born in New Zealand, but British physicist. And surprisingly, he won the Nobel Prize in chemistry. So his work is much more related to the scattering theory as well as the nuclear physics, but he obtained or he won the Nobel Prize in chemistry. Now, last slide. This is the beautiful picture of physics department I've taken in one early morning. Lot of mist and lot of mist in a morning day in a winter, and the sun rays are scattered by mist. So this photograph of physics department is appropriate for this discussion, that sunlight is scattered by a morning mist in a winter morning. And the same morning, I have taken a photograph in the garden of a department. Thank you very much for patient hearing. Thank you very much.